All right. So we've been doing a lot of formulas and deriving and those sorts of things. Let's actually do a problem with some numbers so you guys can see it. Let's do a cannon problem. So it says a cannonball is fired from the ground at 120 meters per second at 30 degrees above the horizontal. And how far does it travel? We could also ask how high does it go? We could ask how long it's in the air as well. These are all questions you could get on this, but we're going to go ahead and do how far it travels, and we'll find a bunch of the other stuff in there as we do it. So let's just draw a picture to get a sense of what's going on first. Here's the ground. We'll do a cannon there, and we'll have a cannonball shot out of it, and we'll have it come up and come down and hit the ground. And we know that it has some initial 30-degree angle here. And this 120 meters per second is at that 30 degrees. But we don't know what its velocity is in the x direction. We don't know what its velocity is in the y direction. So let's go ahead and do those calculations first. They're worked into a lot of our formulas, but I think it's good to separate these sometimes. So the initial velocity in the x direction is going to be equal to, it's like one side of the triangle, right? We're going to find the horizontal component here. So it's just V0 times the cosine of 30 degrees. So 30 cosine times 120 gives me 103.9. We'll call it 103.92 meters per second. We can round those off later. My velocity in the y direction is the initial velocity times the sine of 30 degrees. So we'll just do 30 sine times 120. So that's going to be 60 meters per second. I'm sorry, we got to go ahead and put that 120 there, and that 120 there. So I kind of did a little cheat there, substituted in. So I have my initial velocity in the x and y direction. Now remember, if we want to know how far it goes, it can only travel forwards as long as it's in the air. Time is the same for both of these things. So let's go ahead and remember, we have a formula. The ball is going to travel upwards from here. And I know this is off the ground, but just pretend it's at ground level for this question. It's going to travel up, and then it's going to travel back down. So we need the time up and the time down. Remember that our time total was equal to 2 times the initial velocity in the y direction, negative, divided by g. Okay, so let's go ahead and substitute in 2 because it's up and down. The initial velocity in the y direction was 60, 60 meters per second, divided by negative 9.81 meters per second squared. You may have wondered why that was negative before. These two negatives are going to cancel out. So 2 times 60 give me 120 divided by 9.81, and I get 12.23. And now we have meters per second divided by meters per second squared. So those meters cancel. This second cancels, one of those cancels. And so we really get the inverse of 1 over seconds, which is seconds. So it takes it 12.23 seconds. And now we're down to the last little piece here. The distance in the x direction is going to be the initial velocity in the x direction times time. So the initial velocity in the x direction was not 120. The component that was going in the x direction is 103.92 meters per second times 12.23 seconds. And I get 1,270.9. Now, if we go all the way back, how accurate can we be? Well, we've got a velocity here of 120 meters per second. It's really two significant digits. 30 degrees, I guess we could call that 30.0 degrees if we were being specific. We might be able to keep three significant digits here. If you were not being super picky about it, those seconds would cancel and you can just put meters there. But I would argue you've probably got two significant digits in each of those numbers. So 3 here, 2 here, your final answer can't be any better than that. So I guess it'd be 1,300 meters if you were using significant digits on that. Now you could say that these were exact and they carried on out and we could go greater, but about 1,300 meters for that problem.